All right, guys, let's jump in. We're going to continue talking about multi-step equations with special solutions. And these special solutions just apply when you have variables on both sides. So that's the only time you have to watch for this type of special solution is when you see those variables on both sides, and you'll see what I'm talking about. Let's consider this here on the left. X equals X. Technically, it's an equation, something on both sides, and it's like the multi-steps we learned yesterday because there's a variable on each side of the equation. So, what's the solution? Does X equal 0? Does it equal 5? Does it equal -2? What does X equal? Well, let's see if we can solve it and figure that out if we're not sure. According to yesterday, we're supposed to move the variable over to one side. So I'm going to move the x's, the variables, all to the left. So x minus x equals 0. That cancels out. Same on both sides to keep the equation balanced. But what is x minus x on that side? That also cancels out, and we end up with nothing on the right. X minus x is 0. There's nothing left. And x minus x on the other side is also 0. The variables disappeared. What are we left with? What does x equal? We'll find out in a minute. Let's come back to that in a minute. Let's look at this other one. X equals x plus 1. Again, we're in the same boat. Let's put all our variables on one side. So if I subtract off the x's and they cancel, do the same thing on the other side to get all those variables moved over. But again, they don't combine into anything. They just cancel out, and I lose all my variables on that side. And on the right-hand side, I just have the 1 left over, so I end up with this. What are we to make of these two situations? We try to get rid of the variables, and we end up with nothing in the equation. Or we try to get rid of the variables, and we end up with some term left over, some constant, but that's it. Either way, our variables disappear. What does that mean? Okay, let's talk about that. We can look at the first equation, and let's reason out. Now, this is not a direct mathematical concept we're learning like we typically do, where it's do this 1, 2, 3 to get a solution or something. We got to process through this a little bit. If 0 equals 0, we got to ask ourselves, is this true? Does 0 equal 0? Hopefully you're saying yes, absolutely, it is. It's a true statement. And then let's back up a step. Let's also consider the original equation x equals x. Let's plug in some values. If x were to equal 10, is it true that 10 equals 10? Yep, that's also true. What if we plugged in x equals -5? Let's plug that into the equation. Does -5 equal -5? Yep, it does. And we can keep going on and on and on if we want. We can plug in as many values as we want. X equals x tells us that any number we plug in for x, it's going to equal itself, which means there isn't a single solution. We're used to finding a single solution for x. There's one number that makes the equation true and balances it. That's what we're finding. But in this special case, if things look this certain way to begin with, we have the same number of x's on each side, or better yet, we have the same equation on each side. It's mirrored on both sides. Then we end up with many, many values that would work for x. Therefore, we have a name for that, and it's called an infinite solution. This is an equation where as you solve, you end up coming to a point where you notice either A, you notice the equation is exactly the same on both sides. It's a mirror on both sides, so that no matter what value you plug in, it's going to make the equation true. Or B, even if you don't see it at that point, you continue solving, and once your variables disappear, which they always will on a special case, what's left over is a true equation. Either of those tells us we've got an infinite solution. Either of those tells us any value you plug in for x will make the equation true. So it's an infinite number of solutions. All right, let's look at the other type. This 0 equals 1, and we're going to start by asking the same question. Is that true? And of course, you're going to say, yeah, Mr. A, it's true. No, it's not. Is this true? Of course it isn't. So we've got a situation where our variables cancel and there is not anything true. There's no variable that can make that true. And even if we back up, we can also see that that's the case. If we come back to this original equation and we try an x equals x plus 1 and just try plugging in some values. If we tried x equals 10, well, 10 equals 10 plus 1. Does 10 equal 11? Nope, that's not true. How about x equals negative 5? Does negative 5 equal negative 5 plus 1? Well, that's negative 4. No, negative 5 does not equal negative 4. And so that we see there is no number that exists that will make the right side true. And that is called a no solution equation. The way it was written, there is no value that can actually solve that equation. Another way you might see that written is like this. A 0 with a line through it, that's called a null set. Null means empty. And when we talk about a set, that's the notation where you're solving some type of equation, some type of function, and you end up with a set of possible solutions. And if you're trying to solve something and you find out that there's no solution that will work, it's called an empty set because there's nothing in the solution set to that problem. And so this is just a way to denote a null or empty set. In other words, nothing will work with this equation, and so you might see no solution, or you might see this 0 with a slash through it. They both mean the same thing. I'm okay if you put either of those for the solution to this type of problem. You can write no solution, you can write the 0 slash, you can even write null or empty set. I'm fine with any of those. If you understand and you can communicate that, that's great. They all mean the same thing. Okay? All right. So let's go back up here and look for a quick second at what's going on. Actually, no, let's just move forward. I'm probably talking too much anyway. Let's apply this and see what happens. So we've got 3x minus 6 equals 3 times the quantity x minus 2. And we're going to start solving this like we would any other equation. There's nothing you need to know how to work differently. We see distributing. We're going to break that stuff out of parenthesis prism. We end up with 3x minus 6. And I copy down everything else that wasn't used yet. And maybe you just noticed something. Hopefully you did. We've got the exact same thing on both sides of the equation. As soon as you see that, you know this is a special case solution. You know that it's an infinite solution. Because any value of x, if it's the exact same thing on both sides, it's going to make it true. If you multiply x by 3 and then subtract 6, you're going to get the exact same thing on both sides because it's the exact same expression on both sides of the equation, and you know it's infinite. If you can see that, you can be done there. As soon as you identify the exact same thing on both sides, infinite solution, you're done. Now, if you don't see that, if you're not quite tracking with that yet, that's okay. You don't need to. You can continue, and it will reveal itself to you. we're going to do what we should always do at this point. I'm going to move all my variables to one side, and I'm going to move all my constants to the other, okay? So there's my variables, and then I'm going to move the constants the other way. And notice what happens. I didn't intend this, but this weird thing happens. Right here, 3x minus 3x. Oh, that doesn't equal any more x's. Those also cancel. So I just lost my variables on both sides of the equation. There's no x's here, and there's no x's left here. And then I look at my terms that are left, -6 and +6. Well, that also cancels out. So as I'm trying to solve, this weird thing happens. I'm going to end up losing all the components of the entire equation. Everything zeroes out. So there's nothing left but 0 on the left. Everything zeroes out. Nothing left but 0 on the right. And so even if I didn't notice before, I can notice now. This is a true statement. Anytime my variables disappear, I just ask myself, is it a true or false statement? And if it's a true statement, that tells me any value of x would work. It's called an infinite solution. If I'm left with a true statement, I have an infinite solution. Let's look at the other one. Here I've got 4p minus 5 minus p equals 3p. I'm going to do what I always do. There's no distributing, so I'm going to start with combining of like terms. 4p minus p, 3p, copy down everything I haven't used yet. And hopefully you guys are noticing at this point. I've got a 3p on both sides. That's an indicator to us, something that may be going on abnormal. But we're going to just make sure. I'm going to move all my variables to one side, constants to the other, and since the -5 is already over here, I'm going to move all the variables to the right. So I do that, and again, the same thing happens. The special cases will always reveal themselves, because when you try to put all your variables together on one side, they all cancel and disappear. I'm left with -5 on the left, but on the right-hand side, the p's all canceled. Remember, there is something there. If everything cancels, that means it's just 0 on that side of the equation, but there is a value, it's 0. You're in the same boat now. Ask yourself, my variables just disappeared. I know it's a special case. What does that last statement tell me? Well, it's a false statement. -5 definitely doesn't equal 0, which means it's a no solution. Okay, and you could also have noticed it right up here and stopped right here if you know what you're looking for. And what that is I have the exact same amount of variable on both sides, but on one of the sides, I'm adding or subtracting some value to it. That tells us right there, this has to be a no solution, because any value times 3 minus 5 can't equal itself times 3. That's illogical, it makes no sense. No number when multiplied by 3 is going to stay itself when you minus 5. It's not going to stay the same thing on both sides. The left side's going to get smaller when you minus off 5. The right side's going to stay the original 3 times the number. It's not going to be equal. It has to be a no solution. So anytime you see the same variable on both sides, exactly the same, and you've got something subtracting one of the two sides, that's the early indicator that it's a no solution. But remember, guys, you don't have to remember that. It'll always tell you. Just keep solving until your variables disappear, and you'll either have a true statement that's infinite or a false statement, which tells you no solution. All right. And I just went through that. I kind of just talked through that for you guys. So let's just look at it real quick with some working out. Now, if you guys see this, I kind of did this on purpose. Can you tell right now, are we going to end up with a special case? And if some of you are saying, yep, you just said that, Mr. A, they're the same value on both sides. Okay, I kind of tricked you a little bit just to make sure you're awake. Notice, they are not exactly the same. 5x and -5x are not the same. This will absolutely work out. So don't fall for that trap. They have to be identical. Okay, so let's work this guy out and see. If I move all the variables, I'll move them all over to the right-hand side since I've already got that -4 constant. All my constants are already on the left because that's the only constant I have. So I'm going to move him over. Well, -5x and -5x do not cancel. They combine to a larger group of bad guys. And so right here, I've got just a classic traditional equation to solve. Divide off the -10. Negatives cancel. So the x stays in the problem, and I've got a value as my answer. Okay, and yes, I can reduce that. I'm just focusing on other things at the moment. So there you go. That's a single solution. That's what we've been doing for the last, I don't know, week. Okay, let's look at the next one. I see distributing, so I'm going to knock out the distributing. I get to 6m minus 24. And I'm just going to copy over everything else. Oh, there's some, I didn't even notice. Not even paying attention. I've got like terms there I can put together. I'm going to do that now. So I've got my 5m and my m, 6m minus 24. Okay, anybody notice anything? Yeah, that's kind of painfully obvious, huh? I just came upon an identical equation or expression on both sides of the equation. As soon as I see that, I know what I'm looking for. I recognize, I hate that highlighter. I recognize the infinite solution. But if you're not sure, if you didn't notice that, it's okay. It'll always show you itself. I'm going to move all the variables to the right. It really doesn't matter which way I go. I just picked going to the right. So if I'm minus 6m off both sides, that's when I notice. They end up canceling, and all my variables disappear. Once you see that, keep working, because the next thing will tell you if it's an infinite or no solution. Move all of my constants over to the other side, and if they also cancel out, they reveal they're the same value, and they're going to cancel also. I see that everything canceled on the left, everything canceled on the right, and at that point, I should also notice infinite solution. It was all true. And then we just keep going. 6p and 2p, minus 2p. Hopefully right here, you're already seeing what you should see. I hate the highlighter and the pen. 4p minus 3 and 4p. There's no way those can be the same thing. If I multiply any p-value by 4, if I take away 3, it can't remain what it was originally. It's going to reduce by 3. So the left and the right can never possibly match. That tells me I've got a no solution. I'm adding or subtracting something to the exact same amount on both sides, but only subtracting off one side. That's always going to be imbalanced. And again, if you didn't notice it, it's okay. As soon as you go to cancel variables, they always disappear, and I'm left with -3 equals 0. And at that point, it should be also easy to tell, no solution, because that's a false statement. All right, I have talked enough. You try right now. There are 6 problems. Identify the single solution, no solution, infinite solution for each one. And as soon as you get to the point where you can recognize a no solution or infinite solution, you can stop work, and then that is your answer. You're just telling me it's a no solution or infinite, okay? And by the way, I can already foresee for the quiz on Friday, I don't want to see this. I don't want to see infinite solution, and then you just move on. And it's like, oh, Mr. A, I could just look and tell. Well, you're going to have no solution worth of points on each of those problems if you don't show me some work. So make sure you show work. Do some amount of writing, of simplifying, of working through the problem until there's some step that makes it clear you can tell. Probably should even write a note or something to point it out. It should be clear to me that I know what you're doing. You're not just taking random guesses, okay? So show me some work. All right, go. Make sure to pause me if you haven't yet. All right, let's dive in. I've been rather talkative, so I'm just going to shut up and do some work now. You should have paused me and did all 6 of these. Let's dive in and see. Okay, first one, 3x minus 2 and negative 3x. Did I catch you on that one? Notice the variables were positive and negative. That is not going to be a special case. When I move those over, and I'm going to end up with negative 6x equals negative 2. Dividing off the negative 6, those cancel, and 2/6 I see as 1/3. That is a normal single solution. Next. At this point, I'm fine if you say, yep, right there. That's an infinite solution. Got the same thing on both sides. Okay, next. We got 12p minus 4. 6 and 6, 12p plus 1. Oh, I'm noticing the same variable. That's going to be indicative to me. Again, you can stop right here as long as you make it clear to me you know what's going on. So right there, that tells me that's a no solution because I've got different values or a different amount. Adding to 12p. Therefore, there's no possible solution. Whatever 12p is for any p value you pick, you can't subtract 4 and also add 1 and have those numbers be equal. So we know that's a no solution. Okay. All right. Next, I'm going to distribute there. I'm going to get my 16m minus 10. Oh, and I'm just going to rewrite that and put the 16m up front and the 10 behind it, and that makes it really clear. Oh, I meant to make it an infinite solution, but I made a mistake. So you guys shouldn't have seen the infinite solution. So at this point, oh, never mind. Ha ha ha, it's a no solution, and I'm tricking myself. Oh, I feel a little sheepish. So my variables do cancel, leaving a negative 10 on one side, a positive 10 on the other. What does that tell me? That's not equal. That's a no solution. All right. Right here, since the 2 is dividing everything, I can cancel that by multiplying. We just learned that in class yesterday. Oh, and notice, if you're going to multiply the entire side, that's something we need to learn. I need to probably throw another example of this on tomorrow's lesson. Everything has to be multiplied by 2 on the other side. Not just one of the terms, but all of the terms. So when I multiply the 2 and the 3p, 2 and the negative 4, and I immediately see it's an infinite solution because it matches exactly on both sides. And last, okay, if I'm going to subtract off the 5x there, nothing matches with my variables, so that tells you right away this is going to be just good old-fashioned single solution, and you got to work through it. Okay, hope that makes sense to you guys. We're identifying our normal single solution and working it out, or identifying an infinite or a no solution. All right, peace out.